hi everyone. Oh, great. I think there might be a sound returning. Is it back? Let's see if this is okay. So I just want to ask, if the sound's okay, can you please type into the chat, send a message to chat relay and say that the sound's working. And then my colleagues, yeah, it's all good? Take that as a yes. Because if I'm from phones, it's a little bit hard for this exact road again. This is if I post. I was first attracted to working with because we didn't have a
Oh, hello. We're having a little bit of technical difficulties here. I'm currently trying to work that out. Are
I
you here,
think
patients?
uh, I think Professor Lowe may be back now. We can
Yeah.
pass it back to him.
Oh, Professor Lowe, did you want to say anything else?
Yes, I'm back. Okay. I don't know
Okay.
what just happened. The danger of doing these things from airports, of course, is that the connection's not stable. Sorry about that, guys. But right, that's actually because I just finished a week visiting a math camp out here in Brazil. Math is worldwide. But in any case, yes, I just wanted to say we're very happy to work with Math Kangaroo. At some point, they might have a guest who will show up. When he does, he's a fantastic guy, and he has actually been helping as a math director, working with Math Kangaroo for many years. But with that, the way that this live stream works, if you've been here on our things before, the standard way is if you want to talk, just send a message to chat relay on everyone else's screen except mine. That will show up, and it will be a hoot. With that, I'll drop off and I'll pass it to our very experienced and very interesting co-hosts, Eli and Alan. Alan, I thought you were just talking just now, so why don't you take it from here?
Yeah, absolutely. So hello everyone. My name is Alon, and I am so glad to be joined here by Eli, who is a three-time Amy qualifier and a USAMTS, meaning USA Mathematical Talent Search, perfect scorer. And he also currently is taking graduate level math courses at the University of Connecticut. Besides that, he loves music. He loves playing percussion, just like me, and he has won many national and international contests on marimba. Not like me, much better than me. And he also loves doing Rubik's cubing, playing ping pong, tap dancing, and playing chess. So, what an amazing person.
Thank you so much, Alon, for that awesome introduction. And so now I might as well introduce you. I'm Eli, and I'm so excited to be working with Alon, who is a Washington Math Counts Nationals qualifier. He got a perfect score on the AMC 8, and he's a six-time AIME qualifier. And outside of math, he also enjoys web development and playing piano and snare drum, like me as well. So really awesome to work with him. But I think I'll get started on the icebreaker for today, I suppose we should do before we get into some of the math, which is your favorite property of 2025. This is a pretty cool year. You may know some things about it. So if you want to send some things that you know about 2025 to the chat, we can read about those. But first, Alon, what are some of your favorite properties of 2025?
Ooh, I'll just start us off with a pretty basic one. It's that it's a perfect square. So you can draw a square with side length 45. And if you were to do that, the area of the square would be 2025. So 2025 is 45 squared. And 45 itself is a pretty cool number too, because 45 is a triangular number. So what that means is that 1 plus 2 plus 3 plus 4 all the way up till 9 is equal to 45. And that's a pretty cool property, I'd say.
Yeah,
Meaning
it's
that
kind
you
of,
can,
well, it's just kind of cool that 2025 is a square number. So it's like a geometric number. And then so is 45. It's a triangular number. It's like 1 plus 2 plus 3 all the way down to, is it 9? Yeah, I think so. So, oh yeah, you have that on your screen. And so it's also a triangle. And so we have like both of these geometric things happening at the same time. And there's actually a third geometric thing happening, which is something to do with cubes, because now we have the squares, we have the triangles, but we can also get cubes in here, because actually 2025 happens to be 1 cubed plus 2 cubed all the way up to 9 cubed. So interesting, 45 was 1 all the way up to 9, and now if we just cube all of them, we get 2025 again. It's not really a coincidence, but it is a really cool fact. And so you can imagine, stacking a single cube on top of another cube of side length 2. This is hard to draw in real time, but you know what I mean. This type of thing. And so you just keep on doing that all the way down to a cube of side length 9. And then if you add up all the little unit cubes, this volume would be 2025. So that's pretty cool too. We have all this geometric stuff going on.
Yeah, yeah, absolutely. And I also want to mention, back to the perfect square thing. This is a pretty rare occurrence nowadays because the last perfect square, I believe, was 1936. And so that was before World War II, during the Great Depression, actually. The next one is going to be in, I believe it was 2116. Is that correct? So past this century, past this century. So we're not going to get another number like this for a long time. So you better cherish it while it lasts.
Indeed, and I'm not seeing very many new properties in the chat, so I'll just mention one more. It's not really like the other ones, it's not very geometric, but it is pretty cool, and it's something that one of my students in my number theory class actually showed me. And it's that if you take 2025 and you take a square root, so you get 45, happens to be a perfect square, and then what you do with 45 is you say, well, I'm going to make a new number. I'm going to take 1, and then I'm going to put 2 2s, and then I'm going to put 3 3s, and then I'm going to just keep on going until I have 45 45s. So, a lot of 45s. And so, 44 44s, 43 43s, and so on. And how many digits does this have? Well, it turns out it has 2025 digits. And that's pretty awesome. And actually, 2025 is the only number with this property. It's the only number with the property that if you take its square root, and it's an integer, so it's a perfect square, and then you list out this big number like this, you'll get the same number of digits as the original number. That's pretty awesome. I don't know how anyone ever noticed that, but it's really cool.
Wow, that is amazing. Wow. That is really, really cool. Because, yeah, if you go to the next number, like if you were to go and add 46 46s, you would be adding more digits than there are between 2025 and the next perfect square. So it would start being larger than the corresponding perfect square. And then before
Yeah,
that, it's smaller. So that's the exact number it intersects that.
yeah,
Wow,
it's
that's
the
really cool.
intersection of two curves here. So it's the only time that this ever happens, and it just happens to be at 2025. Feels so random, but it just works out. And this is actually a fun exercise for you to do. Try to calculate how many digits does this have. It's not that hard, and you'll end up proving that it is actually 2025. So really, really cool stuff. I think that's my favorite property of 2025 now that it was shown to me. But the other ones are also really cool. But with
Yeah,
all that being said,
oh,
y-
yeah, my thing was just much simpler than that. It was the sum of the digits of 2025 is 9, which appears here. That was what I was going to say, which is not nearly as cool as the thing that Eli just showed us. But there it is, yeah. But yeah, go ahead, Eli, if you want to get started.
yeah, I think maybe we've talked enough about the year, and we should think about the new math that we're getting this year. And let's start with question number 2 from the Math Kangaroo grades 5 and 6 test. Okay, so we have a picture. Here's a bunch of pictures, and it's a hopping game. Every fourth square in the game is the same. So we actually see that happening, like 1 and 5 are the same. They're both 2 feet, and then 2 and 6 are both the left foot. And then we want to know on which of the following squares will there only be a right foot. So like this is just a left foot, this is just a right foot, that kind of thing. So it seems to me that, well, if this is happening on the 4th, then it'll happen again on the 8th, right? And then on the 12th, on the 16th, and on the 20th, because each time we're just adding 4. It happens every 4. Just like 2 was the same as 6, was the same as 10. This is just going to be 4, and then 8, and then 12, and then 16, and 20. And so we can just look here. The only ones that appear on that list is just option C. The other ones are not multiples of 4. We see that these are just multiples of 4, so they're not the right answer, and it looks like we just get C. And are we correct? Looks good to me. So I think, Alon, you can take the next one.
Amazing. Awesome. Right. So this next question is pretty interesting. Which of the strips should be placed in the rectangle in the picture so that each child is holding a different kite? So we have two children, two kites, and we want to make sure that each child is holding a different kite. So we don't have two children holding the same kite. Right. Now, what I want to do here before we get started with this is I want to just kind of label what each of the outputs, like what the top part of the rectangle and also the bottom part represents. Let me show you what I mean by that. So in this, if we have like a rectangle, what this is basically saying is that this here and this here are going to be connected. And then this is one kite and that's another kite. So these two are different kites. These two are different people. And then these two are connected. Right. So with that out of the way, let's get started with just looking at some of these rectangles. So looking at A, if we just go in from the left, all right, so we go in, we trace that. It's going to go up here, and then it's going to go up to the right there. So remember, the right means we go to the left here. So we go back down here. Oh, man. And then we go, oh, look at this. It brings us right back down to the other person. In other words, these two people are literally holding the same string and the kites are just out there in the sky floating away. So that's not right. That can't be right. Let's look at B. Well, in B, we start on the left here. We start going this way. And then we, again, hit the right. So we're going to go back out to the left. And then we go back in here. So now we end up in the middle here. Remember, for the middle, that means we end up going back up to the third one. So we go to the third one. And it leads us up to the top here. Okay, so for now we're fine. What this basically says is that these two are connected. I'll draw that in right there. But we still have to check the other one because for the other one, it could be connected to here as well, and that would be bad. Wait a second. Look at the other one. There is no connection there. It's just blank. Oh, so in that case, it can't be true at all, right? So we're gonna give a big X to that one as well. What about C? Let's look at C. So for this one, if we start on the left, we go up and into the second one. So that means again, we go into the third one here using this rule here. And then when we go to the third one, oh look at that, it goes right back down. Just right back down into the other person. So this is the same pattern as A, where these two people are connected. Let's look at D now. So with D, if we start on the left and we go down here, again, same thing, same pattern. We go here and then it brings us back to the third one. So we go up on the third one. And then the third one leads us up to the left. So up into the left. So here, in other words, the big connection is just from the bottom left to the top left. It's just kind of like a weird path, right? Let's look at the other one. So we start here and we go up there. And remember, when you go up there, wait, hang on. I apologize. I just realized that with the first one, the path didn't end there. Right, so the first one, when we start going this way, and then that brings us out over here, and then we go up to the left here, we don't just end here. We actually have to go back around to the top right. Oh, and at that point, that leads us back up here. So in reality, this one is a connection to this. That makes more sense. So in other words, the girl is connected to the right, to actually, I guess it would be the left kite because it brings it up there, but you know, it's the right connection. So yeah. Now, if we start on the left here, that brings us up to there. Oh, and that's it. It just directly brings us right there. So, wow, that was much easier than I thought. Okay, cool. I thought it was going to be another big journey, but it was far faster than the first time. And with that, we can see that the girl is holding this kite, and the boy is holding that kite, which means that we end up having D as an answer because it works. Okay, let's see if it's right. Oh, here we go. It is right. It's D. Awesome. Eli, you want the next question?
Yeah, awesome job. That was a very confusing question, to be honest. There was just a lot of lines going everywhere, but you did a really great job of breaking down where everything was going and seeing that D had to be the answer. All right, on to question number 6. Mona wants to draw this figure without lifting her pencil from the paper. Interesting. The lengths are given, 3, 1, and 2. What is the shortest total length she could draw? Well, I think the thing you have to realize with this is because you have this connection in the center that has 3 prongs, there's no way that you can ever do this just in one go without retracing your steps at all. Like you could start here and then go here, but then you'd have to go backwards to get to the third one. Because there's 3 prongs here, you can only ever make a choice that goes with 2 of them at one time, and you'd always have to go back to get the third one. And so you kind of just have to say, well, which thing should I retrace to minimize how much I'm retracing? And I think the obvious answer is just the 1 centimeter one. So you'd want to go down the 3, and then go down the 1, and then go up the 1, and then go over to the 2. And so in total, that would be 3 plus 1, which is the first one here, and then another 1, because we have to go backwards, and then another 2 here. And so in total, that would be, let's see, 3 plus 1 is 4, 5, that I think gives 7. And so looks like it has to be B. And it should make sense to us here because like it can't be 6, because if it was 6, that's just 3 plus 1 plus 2. That would be if it was possible to just do this whole thing somehow without retracing our steps. But that is just not possible. And so if we want the shortest possible length, it just so happens B, which is 7, is the next smallest answer. And since it is the next smallest answer, it has to be the right answer because it is achievable, but A is not. And so that looks like B has to be right. And let's see. Am I correct? I am. Awesome. Back to you, Alon.
Yeah, okay, this is an interesting question right now. So there are 6 boxes on the truck as shown on the right, so here. A worker puts them on the floor. He takes one box at a time, but only takes a box if it doesn't have another box on top of it. So with this first one, you can only take the E and the F to start with at least. And he places this box on the ground or on top of another box. Which of the following stacks could he not build? Oh, that's interesting. Wait, if I understand this correctly, can't you just put all of the boxes like on the ground separately and then rebuild it from the bottom to the top for anything? I don't see where there could be any
I
such
think I think you're
restriction.
not allowed to move the boxes once you put them on the ground. So like you can put down F, but then you can't move it after you put it down.
Oh, there it is. Right. So he so he can only take a box one at a time, right? That makes sense. And then afterwards he can't lift it up again afterwards. Okay, that makes a lot of sense. That's great. Perfect. Now that we have that out of the way, let's get started with this. So with A, let's think about how we can build A. Well, with A, we want to put the E first, and then the F, and then C, and then D and A, and then B. And it seems to me like it's possible to do that, right? Like first you start with the F, so I can like think of like crossing out the F first, or sorry, you start with the E first. First you start with E, just cross it off. Then you go F because that's next on the list, and that's fine again because both of those don't have any dependencies above them. Then C is now available because both of them are off, right? So we can do that. And then D and A are both available as well, so we can also do both of them. And finally, B is just there, so we can put it on there pretty easily. Perfect. So A works, meaning that it's bad. It's wrong because it works, right? And for B, let's think about it now. So for B, we can first do E and F very similarly to A, right? We can just cross them off immediately on the ground there. And then D is now possible because we did F, right? So we can do D right there. And now C is also possible because we removed both E and F. At this point, A and B, you can just do them however you want. But in this case, it tells you to do A and then B. And that means that B, the whole option B, is possible. So unfortunately, B is not the answer either. We want the stack that cannot be built. Let's look at C now. So with C, we want to build E and an F first. Again, as usual, we can do that always because E and F have no other restrictions. Next, C is now open because both of them are off. And then A, now this is when it gets interesting because what it wants us to do is A, B, and D. It wants us to put those ones, right? Now we can put A, but the next one it wants us to put is actually B. So in other words, we have B and then D on top of each other. And here it wants us to put those in the same order. And that's not possible, I think, right? Because what we need to do is to put D first and then B. And so, for example, if the stack was something like D and then B next to it, or D and then B on top of it, or even like D here and then B on top of A or something, that would be fine. But because D relies on B over here, and D also relies on B over here, C is just not possible. So the answer, I believe, should be C. Let's look at the answer and see if it's true. And it is awesome. That's amazing. Yeah, I
All
don't have
right.
two.
I did actually just want to mention something because I saw a lot of people in the chat wondering about D. And so let's see why D actually does work, because it is a little bit tricky. So for D, we can put down the F, right? That F is on the bottom, that's fine. And what may be tricky about this is that the C seems like it's the next thing you put down, but actually you can put down the E first, because the E is just right on top of the F. And so you get those down, that's fine. And then you can put down the C, because there's nothing on top of the C, so you can have those. And then you can put down the D, because it goes there, and then you can put down the B, and then you can put down the A. So it actually works. Hopefully that clears up some things in the chat. So D is not the correct answer, because you actually can do it, and so we have to use option C, and that is our answer. All right.
Yeah, that's a bit confusing for sure. Yeah.
Yeah, it's a little bit tricky seeing how you can actually do option D. But with that said, I think we can go on to question number 10. We have rooms in a hotel numbered in ascending order, starting from 1, and no number is omitted. Okay, so we're not doing this thing where you like skip 13 or something because you think it's unlucky. I guess this hotel doesn't believe in that. So Kangaroo counted all the digits in the room numbers and found the digit 2 14 times and the digit 5 3 times. What is the largest possible number of rooms in the hotel? This is interesting. Okay, so in order to have 2 14 times, we're definitely going to have to be bigger than like 20 or something, because you only get a few 2s. You get like 2 and 12. And then where we're going to get most of our 2s are probably in the 20s, like 20, 21, 22, that kind of thing. So I'm going to start with the 2 condition. And that'll be how many we need to have in the beginning. And then I think the number 5 condition only happening 3 times will tell us what's the biggest possible. So let's see. Certainly we have 2 and we have 12. And then the next ones we'd have are 20, 21, all the way up to 29. You have to be a bit careful here because this is 10 numbers and there's also a 22. So there's an extra 2. So from 20 to 29, there's 10 numbers. And there's also an extra 2 here. So in total, there's 11. And so we have 11 here, and then 12 and 13. Okay, so then that's 13 so far. And then what do we need after that is, let's see, the next one after 29 would be 32. So that would be where we have to stop from the 2 point of view. Like we can't get a 42. If we have 42, then we're too big. So we definitely can't get to 42. Okay, so we know that we're less than or equal to 42, and we're bigger than or equal to 32 from the 2 condition. And so now let's figure out the other condition, which is the 5 happening 3 times. So when do we get 5s? We have 5, we have 15, and 25. And so, oh, well then 35 we're not allowed to have, because if we had 35, then we would have 4 5s. So that means that we actually have to be less than or equal to 35. And so I think, well, not actually, we can't be equal to it. So we're certainly we're just less than in that case. Just less than 35. There we go. And so that means I think 34 would be the biggest we can possibly get, because 35 is not allowed. We'd get 4 5s. And we are still satisfying the fact that we're bigger than or equal to 32, because we get those 14 2s. And so I think this would be option C. We've been getting a lot of C's, but maybe it's still right. It is. Awesome. Back to you, Alon.
Yeah, absolutely. That's a really cool question. But let's go on to this question, which is, wow, a lot of chocolate here. So Mark has 5 boxes of chocolate labeled A, B, C, D, and E. The chocolates in the boxes have been given numbers according to their flavor as shown. So here, just to clarify here, it's A is 1, 2, 3, 4, 5, B is 2, 3, 4, 5, 6, and then the pattern just goes on. So it's C is 3 through 7, D is 4 through 8, E is 5 through 9. Now, he ate most of the chocolates, so the picture below shows what's left. What is the label of the box marked X, where X has 5, like the only chocolate left in box X is 5, and then it goes 4, and 3, and then 2, and then 1. Wait a minute, all of the original boxes have a 5. So shouldn't the answer just be all of them? How can we even distinguish between these? Oh my God, that seems impossible. But wait a second. Let's look at the other boxes. Well, see, if you look at this box, for example, the box number 1, there's only one box that has 1 as a chocolate. So that means that this one has to be A. Similarly for this one, well, actually for this one, there's 2 of them that have 2s. So A and B both have 2, and the other ones don't have a 2. But we already used A. So that means that this one has to be B. Similarly for 3, there's 3 boxes that have a 3 in them, A, B, and C, but we already used A and B, so that one has to be C. And similarly, that one has to be D, because there's only 4 with 4, and we already used 3 of them. And then X has to be E. Quick note here that this is kind of funny because he basically just ate all of the chocolates except for the worst one in each of the boxes. So he ate 2, 3, 4, 5, 3, 4, 5, 6, and so on in each of them, and only left the worst chocolate in each of them. Seems like he could have done better if he just ate all of the ones from the better boxes and left more in the worst boxes, but that's his choice. Eli, do you want to take the next question?
Yeah, absolutely. So that was really cool how you could figure out which one still needed to be the one that had 5 left, even though they all had 5, just by working backwards. But now we can move on to question number 14. We have a nice loop here. I wonder what that's about. So each of 16 circles contains a number, okay? And numbers in neighboring circles have to differ by 1. And okay, that's fine. So like if this was a 5, then this could either be a 4 or a 6, that kind of thing. One of the circles contains the number 5, and another one contains 13, but, well, they're not telling us where they are. Okay. How many different numbers are written in the 16 circles? That's really interesting. So it doesn't really matter where I start. Let's just say my 5 is here, because it doesn't really matter. I could just rotate this. And I have to figure out where my 13 should be. Well, here's one interesting thing. I'm able to decrease and increase. Like I could go 4 and then back to 5 again, right? But let's just see what happens if I do that. If I go to 4 and then 5 and then I try to get to 13, well, let's just imagine I increase all the way from here. Well, then I'd get 6, 7, 8, 9, 10, 11, 12, 13. Okay, well, yeah, kind of encroached on the other loop there, but this is 13. A little hard to see. But what goes wrong now is if I try to get back to 5. Because I'm at 13 now, so, okay, if I decrease, I get 12, 11, 10, 9, and 8. And, okay, that doesn't work because 5 and 8 are actually 3 apart. So I think that means that, well, if I ever go down and then try to go back up, then it's going to take me too long to get to 13. Because once I get to 13, I'm not going to have enough space to get back down to 5. So I think that means I just have to immediately go right up to 13. So let's get rid of all this stuff and start back again from 5. And I think now I just have to increase. I have to go 6, 7, okay, 8, 9, 10, 11, 12, and 13. And then now, does it work? Can I decrease? Well, let's see. 12, 11, 10, 9, 8, 7, 6. Yeah, it works perfectly. We get 5 and a 6, and so those are 1 apart, and all of these are 1 apart. It goes up to 13 and back down to 5. So it works out. And how many different numbers are written? Well, everything from 5 to 13. So how many numbers are there from 5 to 13? It's a bit of a tricky question. You might say, well, it's 13 minus 5. So 8. Well, 8 isn't actually one of the answer choices, so maybe that's why you know it's not 8. But the reason that it's actually one more than 8, which is 9, is because I'm kind of counting the beginning and ending, not just the difference. So the way that I like to do it is I think about just subtracting 4 from everything. And if I do that, then now my list of numbers goes from 1 to 9, right? 5 minus 4 is 1, and 13 minus 4 is 9. And so the list of numbers from 1 to 9 obviously has 9 numbers in it, not 8, even though 9 minus 1 is 8. Hopefully that makes sense. And so looks like option A. Am I correct? I am. All right. Back to you, Alon.
Wow, that was a really awesome solution. Thank you so much. And I guess with that, let's go on to this question where we're going to be exploring the Braille system, which is used by people who are blind. We're in down the digits 0 through 9 are represented by a set of black and white dots as shown here. So they showed us 0 through 9 here. For each of them, we have 6 dots in total. And out of these, some of them are white, some of them are black. And the question asks us, how many different two-digit numbers have exactly 5 black dots? Now, the key here is we only really care about the number of dots there are, right? It's not asking us like how many ways to arrange dots or anything. It's just how many numbers contain 5 black dots. So I think to make it organized for ourselves, let's sort these into buckets based on how many black dots each number has. So 0 has 3 black dots. 1 has 5 black dots. 2 has 4 black dots. 3 has 4. 4 has 3. Oh, that's pretty funny. And then 5 has 4. 6 has 3. 7 has 2. 8 has 3. And 9 has 4. Is that right? Yep, that's right. Now at this point, let's put this into buckets. So the ones that have 2 black dots, that should only be 7. Yep. So 2 is just 7. For 3, that should be 4, 6, or sorry, 0, 4, 6, and 8.
I think Alon, I have to interrupt you for a second because the way that our slides are written out, all of the black dots are actually white dots. So I don't
Oh
know if that
no.
I don't know if that changes the answer. It probably does. So just pointing that out
Yeah.
there.
Yeah, you're right. You're
Um,
right. Okay. Thank you so much for letting me know. Yeah, you're absolutely right. The white dots here are black dots actually, and the black dots are white dots. So in that case, we have to remove everything. But actually, let's finish this with these numbers, and I'll show you how to fix that afterwards. Yeah, let's just finish with this, and we can like change it afterwards. So now with 4, which is really 4 white dots now, but whatever. With this one, we have 2, 3, 5, and 9. And then for 5, it's just 1. Now, yeah, as we said, all of the white dots are black, all of the dots are white. So we have to make it so that so 2 black dots really represents 4 black dots. Because if you look at like 7, for example, that we said it was 2 black, but actually it's 4 black here. So if we just erase this and say it's 4, then we should be fine. And similarly here, if we erase and say or actually it's just the same. It's just 3 because 3 and 3 is just the same, right? And then for 4, it should be 2. And for 5, it should be 1. All right, fantastic. So now we have ourselves the actual thing. And we want to make sums of 5. So in other words, we have like we're making 2-digit numbers, and we want the 2 digits to have a sum of 5 when you like convert them into their corresponding number of black dots. So that means we're gonna have basically 2 cases here. The first case is 4 and 1. So in other words, one of them has 4 black dots, the other one has 1 black dot. And that has just one sort of case of that, which is the case of 7 and 1. If you look here, right, with 7 and 1, that's going to give us 4 and 1 black dot, respectively. And here you might say, okay, so that's just one number, 71. Well, also, don't forget you have 17. So that's going to be 2 possibilities, 71 and 17. Now, for the next one, which is a 3 and 2 case, um, this is when it gets a bit tricky because you might be tempted to say, well, we have 4 ways to choose the 3, 4 ways to choose the 2, and then 2 ways to flip them. But the problem is you're actually overcounting a little bit because you have some numbers that are like 0, 2 or 0, 2, 0, 3, 0, 5, and 0, 9. And those numbers are going to be overcounted here because um, these are not actually 2-digit numbers. They're 1-digit numbers, right? So yeah, but it is important to note that 20, 30, 50, and 90 are good. These ones are fine. It's just these ones we want to subtract off. And so what we can do is we can just kind of, for now, ignore the fact that 0 exists, just kind of like treat it like a normal digit, right? And so we have 4 ways to choose the 3, multiply 4 ways to choose 2. And then, so 4 from this category, 4 from that category, and then 2 ways to rearrange them. And that ends up getting 32. And then as long as we just subtract off these 4, we get ourselves the correct number of possibilities for this case, which is 32 minus 4 equals 28. And so the sum in total is just 28 and 2, which is 30. And I believe that's the answer. It should be C. So let's look at it. Yay! It's right. Awesome. That's great. Go ahead, Eli.
Yeah, that is a very tricky problem, especially with the way that it is listed on our slides. But I think the reason that that happens is just because if it's black, then it shows up as clear. So it's kind of hard to see. Anyway, on to the next question. Question number 18. This one doesn't have a formal statement in the slides here, but I'll just tell you what it's trying to say. So we're having these 10 circles here, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're putting in the numbers 1 through 10 into these circles. We're not repeating any numbers. And the idea is we want the sum of this, and of this to be 23. Each of those should all be 23. And the question is, what is in this circle here? Okay, so hopefully that makes sense. Sorry that there isn't a question statement. But I think we can still figure it out. So the way that I would like to think about this is, well, I know exactly what appears in the whole grid. And I wonder if I can use that to my advantage, even though I don't know what any particular numbers are. So, well, if I know what everything is, I know what like all the numbers are in total, then I know what their sum is. I know that the sum of everything in here has to be, 1 plus 2 plus 3 all the way up to 10. And I can calculate what that is. If you remember from before, actually 1 plus 2 all the way up to 9 was 45. That was related to 2025 because 45 squared is 2025. So I add 10 to that, I get 55. So that's what this sum is here. And then how can I use this information that the sum of this, and of this are all 23? Well, what's actually really cool about that is that this thing that we want, this thing with the question mark in it, is the thing that overlaps. And so I can add, this plus this plus this, and what I'm getting is these 3 plus these 3 plus these 3, so whatever those are added together, and then this 3 times, right? I'm getting whatever this is, I'll call it x, just so it's less confusing, 3 times. And so I get 3 times x plus these 3 repeatedly. Like those 3, I don't know, call this A, call this B, call this C, in terms of where they are. And then what kind of the key thing I have to do is, I actually have to get rid of one of these x's. I have to move one of the x's over, because I want one of those x's to fill out the grid. Right? I want 2x plus A plus B plus C. And what that's going to do is, well, this is my A, this is my B, this is my C, and this is my x. So that fills out the whole thing, right? This x plus A plus B plus C has to be 55, because 1 through 10 were exactly the numbers in this grid in the first place. And so 2x plus 55 is equal to what? That's the sum of this, and of this. But all of those were 23. And so this is just 3 times 23. What is 3 times 23? It's like, I think 69. 2x plus 55 is 69. We can solve that. Not so bad. 69 minus 55 is 14. and then 2x is 14, so we have to divide by 2, and we get x equals 7. And I saw a lot of people putting D in the chat as well, so that looks like option D. And are we correct? We are. Awesome. Back to you, Alon.
Yeah, yeah, absolutely. That's a fantastic question. Now, let's go on to this one, which is a puzzle actually. So we gotta put in the numbers 1, 2, 3, and 4 into each row and column. And in addition to that, though, um, we also want to be able to place these symbols like greater than and less than, so that each symbol shows the correct relationship. So you can see over here with the 1, 2, 2, 1 example, the 2 is bigger than 1, 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 right? Here we only have 5 symbols in total, so we have a 3 here, and it's bigger than all of these 4 around it. And then also this one over here is bigger than that one. Perfect. Let's start solving this. So the first thing we notice here is that these two, both of these two, are smaller than 3. Meaning, because we only have 4 options, meaning 1, 2, 3, and 4, these two have to be 2 and 1 in some order. We don't know which one's which yet, but they have to be 2 and 1 in some order. But what that does mean is that this one, the other one, has to be 4. Because, we already used 2 and 1 here, and 3 is there, so 4 has to be there. And the exact same logic can be applied to this column over here. Okay, it's like the same configuration. So that one's also a 4. Now let's look at this symbol over here. So you can't have a 1 over here, because if there was a 1 here, it would be bigger than something, so it would be 0, and we don't have 0 as an option. So that one has to be a 2 for it to work, and this one has to be a 1, because that's the only possibility for 2 to be greater than, right? Similarly, this one's a 1 over here, because, we said it has to be 2 and 1 in some order. Only found out that one's 2, so that's to be 1. And now, let's see, how do we solve the rest of this? So looking at this, we every row and column, not diagonals. Okay, so now let's think about it now. Let's look at this row, this cell right here. This cell can be either 3 or 4 looking at this column, because we have 1 and 2 here already, so these two have to be 3 and 4 in some order. And we already have a 4 in this column over here, meaning that that one has to be a 3. Right? And I think we can do some more logic like that. Like over here, or wait, over here, this column, this cell over here, remember it has to be either 1 or 2 from this column, but it already has a 1 from this row, meaning that this one has to be 2. And that also gives us this one as being 1 for free. That's fantastic. Also, this one over here has to be a 4 now, because we already have 2, 1, and 3, so that's the only one left, right? What else can we do here? This one over here, we have a 3 and a 4 in here, so this one has to be either 1 or 2. But we already have a 1 in this column, so it must be 2 as the other option, right? And that shows that one's 1 because 1 is the only other option left. What else is there? This one over here, this cell, has to be either 3 or 4 from this row, and we already have a 4 from this column, so it must be a 3. And that also gives us this one as being 4 because that's the last possible option from this row. Finally, these last two ones can just be solved by looking at the columns, right? Here it's a 2 because that's the only one left. And over here, it's a 3. And now let's just do one final check. Make sure we have everything satisfying everything. So on the rows, we have 2, 3, 1, 4, all different. 4, 1, 3, 2, all different. 3, 4, 2, 1, all different. 1, 2, 4, 3, all different. The columns, we have 2, 4, 3, 1, all different. 3, 1, 4, 2, 1, 3, 2, 4, 4, 2, 1, 3. And finally, the greater than symbols all work for all 5 of those. So, wait, which one's the gray circle? I must have missed it.
It's
Bottom
the
left?
bottom left, yeah.
Bottom left, got you. So the answer is 1 in that case, and that should be correct. Let's see what the answer is. We're right. Awesome. That's great. Yeah, Eli, do you
All
want to go
right.
on?
That is such a cool question because it seems like you're not really given that much information. You're only given these like greater than or less thans for like only a few squares, and then you're still able to figure everything else out just based off of like the Sudoku type thing. So that's really cool. All right, onto a more, I'd say, traditional type of math question because it's an area geometry question. Okay, we have 4 touching rectangles, and we want to know the area of this shaded rectangle. Okay, so I don't think this will be that bad because we can actually figure out a lot of the dimensions in here, right? We know that this is 16 and that this is 5, so we actually know exactly what the rest of this is, right? This has to be 11 because it's just 16 minus 5. Okay, and we can do something probably similar with the other parts. Oh, can we? Oh, is this going to be more complicated? No, it isn't. This is fine. 45, this is 5. So we can actually figure out what this height is as well, because the area is 45, which means this side length has to be 9, right? Because 9 times 45 would give, or 9 times the 5 would give 45. So this is 9, this is 5. Cool. What else can we do? Let's see. Okay, so if this is 9, this is 13, that tells us what the rest of this is. Okay, because this is 13 minus 9, which is 4, right? 4 plus 9 gives 13. What else? Okay, we have the area of this rectangle. This height is 4. We want its length. And that's not that bad. 4 times 10 gives 40, so this should be 10. And what else can we do? Well, this whole thing is 16, so this has got to be 6, because I have to make 10 plus 6. Okay, what else? This is 48. This is 6, so this has got to be 8. 6 times 8 is 48. And it feels like we should almost be done. Yeah, we are, because this is a 4, and this is an 8. So that tells me exactly what this side length is. It's just 8 minus 4, so 4. It's pretty cool. What else can we get? We just want the other side length of this thing. Oh, we can do that now, because this is 6, and this whole thing is 11. So this would be 11 minus 6 gives us this 5, right? 6 plus 5 is 11. Okay, so we have 4 and 5. 4 times 5 gives 20. And I guess you need units. I don't know. I'm a mathematician, not an engineer. I don't really care about units, but they say 20 centimeters cubed, or squared, excuse me. So that looks like E to me. Let's see. Am I correct? Looks good. Awesome.
That is awesome. Yeah, let's get right into the next one in that case. So, in this one we have a guy named Damien who wants to fold the net shown to make a cube, and he wants the triangles of this cube to be shaded. He wants a triangle that touch the edges of neighboring faces of the cube to be shaded the same. There we go. Now, how should he shade the triangles of the unshaded square in the net? So we have all of the squares except for one of them have already been shaded, and we have to shade that last one ourselves. So the triangles that touch the edges of neighboring faces to be shaded the same. Got it. So first things first, that's pretty clear, is this here. Actually, let me just draw like a bigger version because I cannot draw on that like a really small square. It's just gonna absolutely kill me. Right here. We have this, and we have ourselves triangles there. So first of all, pretty clearly, let me use a different color. These ones have to be shaded. Pretty obvious because they just straight up touch the other two triangles over here. Unfortunately, that doesn't let us eliminate anything because all of these also have the property. I guess they know you're that smart, so they're not gonna do something like that, right? Now, let's look at these two triangles over here. So these two triangles, they touch these two ones over here. Because you think about it, like when it curls around, these 4 squares are gonna just curl around and like touch each other. It's kind of like a like the 4 squares and like that, right? And the other two ones, these two, are gonna be the two squares that are like what you can like sort of see through, right? Like the other two ones on the front and back, which I can't cover because I only have 2 hands. And so what that means is that this bottom one should be shaded and the top one should be unshaded. So that gives us more information. And that already can allow us to eliminate option E, which, as you guys can see, has the opposite pattern. So that's definitely wrong. Let's go on. Now, what about these two? Now, you might be like, okay, so these two in that case align with these two over here, right? Like these two over here, right? Because these two edges obviously connect. Well, not quite. Look at it. These two edges do not connect. In fact, these two edges connect. Because when it like folds up, then this point over here becomes a corner of the cube. And each corner of the cube touches three faces. And those three faces are this one, the top one, and this like sort of middle one over here. And so these two are going to touch. In reality, what that means is that this one actually touches that one over there. It goes, so this one touches that one up there. And the order it touches it should be the opposite of the order you see here. Because if you think about it, right? So the way I think of it is I think of it in terms of vertices. So this vertex is the same as that vertex because these two edges are the same. And so what that means is that this vertex is the same as that vertex because it's just the next one onwards, right? And so if you look at it here, it's green yellow. Here it's yellow green, and so it's going to be flipped as well, which means that the real shaded one is actually going to be this right triangle over here. And this already eliminates quite a few of them, right? It already eliminates C and D, which for both of these, it's going to be like both of them show us as having neither of them shaded. And it also eliminates A, which has both of them shaded. So we can already tell the answer is B, but just to make sure, let's figure out what these bottom two are shaded. So if you look at it, we can apply the same logic actually. It's symmetrical to see that, let me get another color out. Where's my, there it is. These two vertices are the same, right? Because again, like these two edges are the same. And then after that also, these two vertices are the same. So look at these two vertices and these two vertices using the same logic. So in other words, this left one equals the right one, and the right one equals the left one. So in reality, the left triangle should be shaded, and the right triangle should be kept normal and the same. And that corresponds with B. B shows us having the left one being shaded. So we're good. So I think the answer should be B. See it? And it is. That's great. Eli, take it away.
Yeah. Awesome job there. All right, on to question number 26. Mary wants to write the numbers 1 to 8 on the vertices of a cube. Very natural thing to want to do. I can relate. She wants the sum of the numbers on the vertices of each face to be the same. Okay, so if this is a face, we want the sum of all of these to be the same as the sum of all of these, and to be the same as the sum of all of these, and so on. She has already written down the numbers 6, 7, and 8. And what number should she write in the vertex marked with a question mark? Okay, this is an interesting one. I think maybe the first thing we want to do is say, well, what's the total sum? Because I think that's a natural thing to do is say, well, what do I actually want my sum on each face to be? So I'll consider what's the total sum of everything in the cube. Well, I know that the numbers 1 through 8 appear in each of the cubes, so the total sum of everything is just 1 all the way up to 8. I'll use that fact again. 1 all the way up to 9 was 45. We don't have that 9 anymore, so I believe this should be 36. Another way of doing things. Okay, and so if the total sum of everything is 36, how can we get the sum on each face? Well, let's just imagine I added each face together. So I get 6 times the sum on one face, right? 6 times x. I'll call the sum on each face x. But this is overcounting a lot, right? Because, like, for example, these two vertices are shared by these two faces, if I can make that clear. So these two would be shared, for example, but also these two and everything. So how many times are they shared? Well, a single thing over here, a single vertex, is counted on 3 faces, right? Like this vertex is counted in this face, and in this face, and in this face. And that's true for each and every vertex. So when I take 6 times the sum, I get every vertex exactly 3 times. In other words, 6 times the sum is just 3 times the sum of everything in the cube. And so 6 times x, which is the sum on one face, is 3 times 36. Divide by 6. I like that 36 is 6 times 6, so I'll get a 6 over here. And that means x has to be 18. Looking good so far. So that means the sum on a single face has got to be 18. Okay. Now, how can we use this to finish the problem here? Well, we already have a 6, a 7, and 8. Those are like the biggest ones. I wonder if we can use that somehow. Because like 8 and 7 are on one face already. 8 plus 7 is just already 15. And we can only go up to 18. So that doesn't actually leave that many options, right? I mean, if 8 and 7 are on one face, then the only other things that there can be are 2 and 1, because we have to get a sum of 3. The only way we can get a sum of 3 with numbers from 1 to 8 that aren't repeated are 2 and 1. So these are 2 and 1 in some order. And I don't really know how I'll notate that. I'll just say, one of them is 2 and one of them is 1, something like this. And then we can do similar kind of thing with the other numbers in here. Like for 8 and 6. 8 and 6, 8 plus 6 is 14, and that's really close to 18 as well, right? 8 plus 6 is 14. There's only 4 more that we can leverage here. And let's see, well, if this was a 2, then, well, this would have to be a 2 as well, because 2 plus 2 is 4, and then the whole thing would make 18. So that's actually not possible. That means that this can't possibly be a 2, and has got to be a 1. So if this is a 1, and the whole thing sums to 18, then we get 8 plus 1 is 9, plus 6 is 15, and this has got to be a 3. And so, I mean, we could fill out the rest of the grid, but we're a little bit short on time. So I'm going to just stop there. I believe the answer should be C, or 3. And let's see, am I correct? I am. Awesome. On to you again, Alon.
Yeah, let's go on to question 28, where we have Dan who wants to cut a rope into 12 equal pieces and marks the point where he needs to cut. Now, let's just pause there for a second, because if he wants to cut a rope into 12 equal pieces, he's not making 12 cuts. He's making 11 cuts, because if you think about it, if you have a rope and you want to cut into 3 parts, for example, you're only making 2 cuts. So just to make sure you all remember that it's 1 less cut than pieces. Now, Muhammad plans to cut the same rope into 16 equal pieces and marks the points where he needs to cut. And then Maya cuts the rope at all marked points. So how many does she get? Well, okay, so we have 11 cuts from Dan, and we have 15 cuts from Muhammad. So overall, we have 26 cuts in total, and that means we have 27 pieces, and that's the answer. So C is the answer, and we're done, right, guys? We're done. That's all it is. Obviously, nothing else in this problem is needed to know. Right? Oh, maybe not actually. Maybe not. Let's think about it. So let's consider a smaller example. What about 4 and 6? So Dan wants to cut the rope into 4 pieces, and Muhammad wants to cut it into 6 pieces. By the way, the key here is that 4 and 6 share a common factor, which is 2, and 12 and 16 also do that. They share a common factor of 4. You'll see why that's important very soon. So if Dan cuts it into 4 equal pieces, his cuts are going to be here. Let me just do this like this. A bit longer so it's easier. And we have 4 equal cuts. And then what Muhammad does, and I'll do it in a separate rope so you guys can see it side by side rather than being in the same place for now. And that's going to be here, and then here, 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 here. And the key is that while these ones are different from these ones, these 2 middle ones, are the same. And that's because both of them cut the rope into half. They also do a lot of other ones, but one of their cuts is going to be in half. So they share a cut. And that's important because, so even though in this case, Dan would make 3 cuts and Muhammad makes 5 cuts, they don't really make 8 cuts in total. They make 7 cuts. 1, 2, 3, 4, 5, 6, 7, because one of them is shared. So we have to also count how many cuts are shared here. And that is dependent on what common factor is shared here. So Dan cuts the rope into pieces of length 1/12. Muhammad cuts the rope into pieces of length 1/16. And so the sort of like the common factor between 1/12 and 1/16, the least common factor, least common multiple of 1/12 and 1/16. It sounds weird when I say that. Like usually think of integers when I say least common multiple, but in reality, you can apply the same idea to fractions, right? because as long as it's integer multiples of fractions, you can apply the same idea, right? So the least common multiple of these two fractions is going to be 1/4, because for this one, it's it's equal to 3/12, and then it's also equal to 4/16. So what that means is that they're going to repeat, so they're both going to do the same cut for all the multiples of 1/4, which are 1/4, 2/4, or really 1/2, if you want to call it that way, and 3/4. And so three of the cuts are shared. And where we said from earlier that Dan has 11 cuts, Muhammad has 15 cuts, and they share 3 cuts. So it's 11 plus 15 minus 3 equals, what is that, 23 cuts in total? But that's not the answer. The answer is 24, because that's the number of pieces that they have. So the answer is 24, which should be A. Let's see if I'm right. And oh, wait. There we go. I am right. Awesome. That worked. Eli, did you
Yeah, that was really cool and a very tricky problem. It seems like almost everyone in the chat was getting it wrong, but you got it right. And I actually think if I got that, I might have initially made that mistake as well of getting 27, because it seems like you have 11 and 15, and those are relatively prime. So, you think maybe actually there isn't any overlap, but no, there is because of the 12 and 16. All right. On to question number 30. We're going to go a little bit over time, but I think it'd be fun to finish because we're so close. Ava writes a 3-digit number on the whiteboard, and then Brandon writes a 4th digit to the right of the previous ones, and he says, look, the number increased by 2024. What digit did Brandon write? Okay, so Ava writes a 3-digit number. I don't know, call it ABC. And then Brandon comes along and then writes a 4th digit to the right of all these ones. I'll call that D. And he says, well, okay, ABC increased by 2024. So plus 2024 ended up being ABCD. Well, this isn't that bad if we just understand what's going on with like these whole decimal expansions and everything. Because what does ABC mean? Well, it means I have 1,000, I have A 1,000s, and then I have B 100s. Well, no, that's not true at all. That's what ABCD is. Okay, so I'll just do ABCD then. I have 1,000 times A plus 100 times B plus 10 times C plus D. That's what ABCD is. And then for ABC, I have A 100s, I have B 10s, and I have a C. So that's what ABC is. Okay, so now that we have all of that down, I think we can write this out as 100A plus 10B plus C plus 2024. And I actually realized maybe this is not the best way to do this. There might be a way to do this with like an addition using digits and stuff. We'll see what happens. And if I need to reroute, I'm sure Alon can save the day. We'll see. So, okay. No, I actually think this will work, maybe. So one thing we can do is we can rewrite some of these common expressions here, like 1,000A and 100A. We can rewrite to just be 900A on the left-hand side, right? Plus, and then 9dB. And here we have 9C. And we still have a D left. And that's equal to 2024. Okay, so let's see, add some more space for myself here. What can we do now? Well, actually, we have, what is the question asking for? It's asking for what digit did Brandon write? Okay, this is good because this is actually really simple now because everything here is divisible by 9, right? I have 900 is divisible by 9. It's 9 times 100. 9dB is divisible by 9. It's 9 times 10 times b, and then so is 9c. So what's kind of interesting in terms of what's going on here is that whatever this is on the left, it needs to be the same when I divide by 9 in some sense as 2024 over here. Or another way you can think about it is if I do 2024 minus d if I move the d over, that has to be divisible by 9, right? Maybe this is making sense. And so, well, there's not that many options for d. D has to be, either 0 all the way up to 9. And so if 2024 minus d has to be divisible by 9, well, what's the nearest thing to 2024 that's divisible by 9? Well, I think 2025 is. It's 45 squared. 45 is divisible by 9. But we're decreasing, so we can't go up. So we actually have to go 9 below 2025, which is 2016, right? Okay, so if I in 2016, the one below that would be too far away. I'd never get there just by subtracting 9, right? Because if I subtract 9, I would only be at 2015, so I can't go below that. And so the only way that I can get to 2016 as 2024 minus d is 8, right? So I think that means that the digit just has to be 8. And so that looks like option D to me. And it's really cool that actually we don't even care what the digits A, B, and C are. Just by using this reasoning here, we can figure out that D has got to be 8. And so that has to be the digit that Brandon wrote on the board. And so am I correct? Looks good. Awesome. We've finished all the problems. 100% win rate. How you feeling, Alon?
That was fantastic. And actually, I want to just extend that final bit of reasoning you had there a little bit, because with the whole A, B, and C not mattering thing, you can take that even farther, because you don't even need an A, B, and C. You can just say the whole X is the number that Ava wrote down. And then because X is what Ava wrote down, what that means is that what Brandon wrote down is 10x plus D. Because all you're really doing when you have like a number like all these random digits, and you add on an extra digit at the end, D. What you're doing is you're just shifting over. You're basically just adding a 0 at the end of this, which we all know if you add a 0 at the end, it's the same thing as multiplying by 10, right? And then you add D, which basically replaces that 0 with a D in our base 10 system, right? And so overall, when you x D, where x is like any number of digits at all, right? Then it's equivalent to like 10x plus D. And from there, I think it's a lot more intuitive with respect to like the equations. Like this is basically the equation you get, which is 10x plus D minus x equals 2024. So 9x plus D equals 2024. And from there, it's the same kind of logic that Eli was using with the remainder and finding the biggest multiple of 9 less than that number.
Yeah, that's a really great way of generalizing it and getting rid of all those annoying A's, B's, and C's in there, because it actually doesn't even matter that it's 3 digits. It can be any number of digits and it will still work out the same way. All right, I think that is all we have for the live solve today. Thank you so much everyone for coming, and I guess hopefully you'll try out live and you'll come to watch some more of our live solves.
Yeah, for sure. Thank you all for coming. Goodbye, everyone.